Hello, everyone. So here is Canva. And Canva is a design platform where you can design pretty much anything, like social media, presentations, posters, or maybe even a birthday card for your favorite programming language, or maybe a logo for Reactive Summit. And like in many other systems, a lot of interactions with Canva can be represented as response. And as a user, you can, for example, type something in the search field, and that will be a request. And the list of the templates that you can get back is a response. If you click on one of the templates, that's a request, and the updated document is the response. If you edit some heading, that's a request, and the saved document is the response. But the game changes completely once the second user joins the editing. You want to see the changes that other users are making on the design immediately without going and explicitly requesting them. If the second user types anything into one of the fields, you want to see the effects as soon as possible without any wait to avoid any possible conflicts. And my name is Sergey. I work on the gateway team at Canva. And some time ago, our team set off on a journey to enable our users to collaborate freely at scale. And why should you care about scale and collaboration? Maybe you're building the next billion-dollar collaboration startup with RSocket, and at some point you're going to get a lot of user tractions. And you need to make sure that you'll survive when all of the users come to your service. Or maybe you're working on a large established application already, and it has a significant amount of load on users. And you want to empower your users to collaborate in real time. And in this talk, I'll try to highlight our experience, which can hopefully be useful in both of these cases. So let's briefly explore what exact functionality I mean when I say collaborative applications. So here, two users, Alice and Bob, and they both want to edit the same design in Canva together at the same time. And Alice wants to make a simple change, just to add an exclamation mark. And Bob needs to see the change as soon as possible, without going and explicitly asking for that change. Or consider another example where Alice is giving a talk on Zoom. And it's kind of similar to what I'm doing right now. And Bob, Carol, and Dylan are all connected from their phones, and they are leaving reactions and comments to the presentation. And in that case, we also want to see all of these reactions on the Alice's screen as soon as possible. So as you can see, collaborative in this context means that we need to notify our users as soon as any event happens on the backend that they are interested in. And in our case, the complexity of designing such a system, such an application, comes not only from the application domain itself, but also from the Canva scale. Canva has more than 60 million users, and the services need to scale accordingly. And when designing collaborative applications at scale, all of the aspects of engineering need to be considered. And that's the application design, it's the architecture, it's the infrastructure, essentially the platform on which your application is running. And all of these choices is what I'm going to try to focus on today. So let's start from the architecture. And WebSockets are a perfect abstraction for this use case. They provide an abstraction that everybody knows, and they're very similar to normal sockets. You send bytes in, and you receive bytes out. And WebSockets are great, and it's relatively easy to implement message passing for a single service. We can just take JSON payloads, encode them as bytes, pipe them into frames, and send them to the editing server. And that's it. The job is done. But in microservice environments like Canva, there is never just one service. There can be different services that provides real-time functionality. And that can be editing, that can also be live presentations. And in that case, both services need to expose an endpoint. But that would mean that we would need two connections from every single client to two services, which would double the load on the backends. And it also would require twice as many resources. And adding a third service to handle, let's say, push notifications or analytics would require another connection, which means that adding new connection every single time presents a new scaling challenge. And I think you can see the issue right now. And the scaling challenge here is that we want to perform multiplexing of different channels, all of them and put them into a single connection. That way, the number of connections that we have to handle only grows with the number of users and not with the number of backends that support streaming functionality. And the simplest way to solve this is to implement a WebSocket gateway. And the WebSocket gateway can be that backend that accepts WebSocket connections from the users and forwards the related messages to the appropriate backends. So as a gateway, it could also handle all of the infrastructure functionalities, authentication, authorization, tracing, all of that infra stuff. However, you can't just take all of the messages and push them into the same connection without some sort of protocol for multiplexing. WebSocket gateway needs to understand which message each message belongs to. And WebSockets by themselves do not provide that type of functionality. They don't give that abstraction. They only give you a transport abstraction, not an application one. But luckily for us, there is such a protocol already. It's called RSocket. And I'm sure a lot of you are already familiar with it. And it gives you a way to process multiple streams over a single connection. And it provides you with a programming model based on channels. And the biggest difference between RSocket and any other protocol is that it gives you reactive stream semantics for those channels. And it propagates these semantics across the network. And that way, the WebSocket gateway could accept all of the incoming RSocket connections, and it would understand which backend each message belongs to because of the metadata, and would route it appropriately. And that way, for example, both editing and presenting messages can be sent into the same connection, but then the WebSocket gateway would receive the connection, would unpack the messages, and let it flow to the appropriate servers. So let's take a look in details how such a connection could work. So here is Bob, and Bob has just connected to the WebSocket gateway. He just established the WebSocket connection. And within this connection, Bob can create multiple channels. For example, a presenting channel, and the channel for the editing service. And RSocket takes care of creating and managing these channels. And it also ensures the order of messages within them. And what's really important, every such a channel has its own backpressure. But what does it give us? Why do we even care? And without backpressure, everything works in an exactly the same way. Consider a simple stream implementation with no backpressure at all. Most of the time, it's going to work exactly the same. It just red messages flow to the editing service, and the green messages flow to the presenting service. Simple and easy. But it's an outage that makes the difference. It's never possible to avoid outages completely. It's just a matter of time until the next outage happens. And the only thing that we can do, we can restrict the blast radius. And without backpressure, there is not much you can do. If the editing service goes down, it can also bring down the WebSocket gateway and all of the intermediate channels. And that's not a very good situation to be in. One backend is down, the whole system is unavailable. And having backpressure for every single channel separately saves us here. If the editing service goes down, it will stop requesting messages from the clients, and the clients would stop producing them. That way, the messages from other backends won't be affected. They will still flowing as normal through the WebSocket gateway, and it's only one service that is down. Essentially, we managed to restrict the blast radius to a single service. So from the architecture perspective, not only RSocket helps us to ensure that we only have to handle one single connection, but it also makes sure that none of the backends by itself can bring the whole system down. Okay, now that we've looked at the overall architecture, let's zoom down to some specific application components. And quite often when you introduce a new piece of technology into an existing application, you can't just simply follow a standard greenfield approach. You have to fit the new technology like a brick in the wall. Essentially, it has to be consistently inserted into an existing architecture. And for our gateway layer, we currently use Jitter as a web server. And Jitter is not supported by RSocket Java by default. So when we started building the system, the first question was, can we make RSocket work with Jitter easily? And because of the RSocket Java architecture, a new transport can be introduced pretty easily anywhere. And implementing a completely new transport that's not available by default, it's very easy. all you have to do is to implement a single interface. Essentially, you need to understand how we can take bytes and send them into a connection, and also how we can produce a stream of bytes, essentially the data from the client, and not much else. And for any application at scale, observability is also critical. You can't really live in production without observability. And at many conferences, we constantly hear performance, 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 performance. But the cost of downtime is often much, much, much larger than the cost of getting just a bit more resources to support the monitoring overhead. And luckily, with RSocket, you can get both performance and observability. However, with a reactive streaming system, you only think that we only need to care about these errors as a type of frames in RSocket and nothing else. Just measure the errors and the job is done. But unfortunately, it's not that easy. Let's take a look at a conventional application. Let's say a REST API, or even a typical interaction as a request response with RSocket. Every single request can either become an OK response or an error response. We just take the error rates, divided it by the total number of requests, and that's it. We've got a measurement of errors, like the error rate dashboard. That's very easy and is understood by practically everyone. But in the world of streaming, making sense of metrics is much, much harder. And that's because the lifecycle of channels is very different. To start with, we don't even know how many messages we are going to have in a single channel. We might have a potentially unbounded number of next frames. And then at the end, it might either complete with a complete frame or an error. But that's not it. We also need to track the cancel frames and track the cancellations. And we also shouldn't forget that it's a bidirectional channel. That means that we have an incoming flux, all of the frames that are flowing in, and we have an outgoing flux, all of the frames that are going out. And when plotting the metrics or setting up the different alerts, it's very important to distinguish them, because the source of errors on the backend does not necessarily match the source of errors on the client. And these can be completely different metrics. And at some point when deploying a system, you still have to decide on what is going to be that main graph that represents the health of your system. And we found that a good approximation could be just the rate of error rate frames divided by the total number of frames. But an important thing, that it's better to exclude keep alive frames. And that's why keep alive rate does not necessarily represent the user interactions. It doesn't matter whether a user is sending any messages and actually interacting with the system, or the connection is just idle and a user is not touching the keyboard at this point in time. So keep alive is quite consistent and it depends on the number of users, but it doesn't really introduce a lot of information. So excluding them from the calculation increases the signal to noise ratio by a lot. Okay, now let's take a look at the place where all of the requests originate, the browser. And on the backend side, we had to make sure that the tooling fits organically into the whole system. And in the same way, RSocket.js had to fit organically into our front-end ecosystem. And in our case, on the client, we use RxJS for reactive programming, which is the de facto standard for all of the type of interactions in JavaScript or TypeScript. And when I first tried to introduce RSocket.js, I was actually surprised because it turned out that RxJS does not support backpressure. And RSocket.js comes with its own set of classes that do support backpressure. And the decision of Rx engineers totally makes sense to me. When a user is the source of events and I'm the user, I'm typing on the keyboard, you can't really apply the backpressure to me. And in that sense, there might not be a lot of reasons to support backpressure in JavaScript library. And to keep RSocket.js compatible with the rest of our ecosystem, we convert flowables, the classes that support backpressure, into observables, the classes that don't support backpressure. And this is the great place for you to decide on your backpressure strategy, and in particular, how exactly your application is going to behave when the server is overloaded and is not able to accept more messages. And you can decide that per channel, and that's amazing because you might decide that for your analytics channel, you can just drop messages. That's fine if some events do not arrive. But for your editing channel, if the server is down, you have to stop the users as soon as possible. You can just tell them that you can't continue editing because otherwise you might suffer data loss. So you have to stop the users as soon as possible. And backpressure is great when one of the backends is down, but there is always a chance that but one of the WebSocket gateway instances goes down. And in cloud, anything can happen. Any instance can restart at any time, or the user might lose Wi-Fi, or they can close a laptop lid, or a proxy can restart. Anything can happen. And in this situation, the clients would need to reconnect, essentially to establish the connection again. And this is a part of the code that has to be implemented very carefully at scale. And the very first thing to consider is exponential backoff. You don't want the clients to constantly try to reconnect, because as they disconnect, they can just keep trying and trying and trying, increasing the load to some crazy numbers. And instead, you want to increase the wait times gradually if the servers do not respond. For example, try after 2 seconds, then 4 seconds, 8 seconds, etc., until you reach a certain limit. But it's also very important to not forget about jitter, because when the servers are finally up and running after an outage, the last thing that you want to happen is for all of the clients to come together at the same time at a big wave after 16 seconds and destroy the servers altogether. And jitter helps to avoid the situation because it adds randomness. And because of this, some clients will try after 12 seconds, some clients will try after 17 seconds. There is not that single time when all of the clients come together at the same time. And when working with RSocket on top of WebSockets, the browser felt like a huge point. And I personally felt a lot of pain because, like, looking at this screenshot of the messaging tab, I'm not really sure what is exactly happening here. And I'm pretty sure that nobody can really decode RSocket frames with their naked eyes. And to solve this problem, we introduced and created a new extension that we open sourced that essentially decodes the RSocket messages and presents them in a very readable form. And that's also very useful for education, because when you bring new people and you try to explain what RSocket is, how it works, and what all of the reactive programming is about and how the protocol works, it's incredibly useful to visualize what is exactly happening. And it helps a lot with debugging. Okay, let's take a step back to the backend and talk about load testing for a bit. Because once your application is ready, once your system is ready, you want to launch it, but before that, you want to test it. As an engineer, it's very easy for me to write a test that would generate a lot of load. I can create lots of channels with 1 megabyte messages that are sent every 100 milliseconds. And that can test the system, but it can vastly misrepresent the load for many applications, because very often the connections are idle and the messages that are flying through the connections are very small. For example, if I'm editing a Canva design right now, I'm not going to send a lot of messages all at once, and they might not be heavy. I might be typing some heading, and that's actually very small payloads. And most of the time, the connections are going to be idle. However, every single connection takes up memory. So it's very important not only limit the CPU usage and essentially the amount of CPU that you need, but also to understand how many connections every single server can handle, because every single connection is a user that takes some memory in the heap. And once you've discovered the limit, that number of connections that a single application can handle, it's also important to implement load shedding, because at some points when you have an influx of connections, it's much better to keep serving some number of users than to serve no one. And that way, if you have a recent influx of connections until your auto scaling kicks in, you still want to survive at least for some number of users. And I hope it's much clearer now how you can build application and some of the reliability controls in your application. So let's now talk about infrastructure. And the very first and very crucial part of any reliable infrastructure is load balancing. And here is the architecture. Users are connecting to the WebSocket gateway, and then the gateway connects to the downstream backends. And here you can see the connections of two types, the connections of type 1 and connections of type 2. And the connections of type 1 are the users that are connected to the gateway. And we have as many connections as we have users because every single connection is a user identity. It's like my tab in a browser. But the number of connections of type 2 can actually be very low. We can just create a single connection between a WebSocket gateway and the backend, and we can create as many channels within that connection using RSocket as we want. And that's another important role that the WebSocket gateway is performing. It takes the responsibility of handling a large number of connections. And it's not something trivial because this server has to be configured accordingly. There has to be enough memory, and you have to be able to survive spikes and handle all of the SSL handshakes. Essentially, load balancing, and the load balancing of connections of type 1 is not really a hard task. Every time a new user comes, we just select one of the gateways and we proxy a connection there. However, load balancing the channels within the connections of type 2 is more challenging. And our first idea was to use a normal load balancer, a pretty standard approach, because there can be multiple targets behind a load balancer. However, we quickly discovered that there is a problem. Consider a situation when there is an increase in traffic and a new backend scales up. It scales up, but it doesn't receive any load. But why is that? And the reason is that behind the load balancer, the backend is hidden from the WebSocket gateway. It doesn't even know that it started. And the gateway only knows about load balancer, and it just keeps increasing the number of channels through the existing connections. So to fix that, we ensure that all of the WebSocket gateway connect to backends directly without any load balancers. But of course, in that case, the gateway needs to know about the addresses of these backends. And that can be solved by introducing a new component which can be a service registry. That way, every time a new backend starts up, it registers itself in the service registry. And then every single instance of WebSocket gateway listens on the updates and connects to the new backends directly. And that way, we can balance the load. And what's very important, the load balancing can now be happening on the application level. Essentially, the application has a number of connections, and it decides which connection the channel would go to. And that's very important because it can be a single connection, but there could be already a lot of channels that a given backend is handling right now. And a simple round-robin algorithm doesn't quite work well in this situation because the channels are long-lived. So consider a situation when a new backend just started, and now we have 50,000 connections to the first backend, another 50,000 connections to the second backend, and just one connection, channels, and just one channel to the last backend. And now, if we continue round robin, we would still increase the amount of channels on the first two backends, and that's not what we want. And one of the alternatives is to use, for example, list loaded algorithm. But again, we can only do that if we have control on the client side, which we do. But no code stays the same forever. Deploying often, at least daily, is now practically a requirement, at least for us at scale. And redeploying an instance that maintains a large number of connections can be a challenge. But what is redeployment? In the essence, it's all about taking the existing fleet of services and replacing it with a new fleet of services. But doing that very sharply can result in a huge spike of connection and a huge spike in latency, because every single client has to reconnect, and the initial reconnection is the most expensive operation. And the standard way to handle it with load balancers is, again, a deregistration delay. Essentially, the idea is that let's wait until all of the HTTP responses finish, and the traffic would naturally flow to the new instances. However, with the long-lived channels, it doesn't work, because it's the idea that they are long-lived. Nothing is going to kill them. And even though the new requests would go to the new fleet, the old connections are not going anywhere. They are long-lived. So instead, the application has to take care of closing the connections itself. And at least on AWS, it's quite tricky. You have to come up with a way to notify the application that it is being deregistered right now, so that the application itself can start closing the connections one by one, allowing for the traffic to gradually shift without introducing any latency or load spikes. And in conclusion, RSocket is an amazing building block for creating collaborative applications at scale. However, the change of the paradigm from request response into streaming presents a number of challenges, especially when it's deployed at scale. And building such services is definitely a hard task. It's hard, but it's absolutely possible, and it greatly improves user experience. So today I went through a set of challenges that we faced building similar collaborative applications with RSocket at scale, and all of the solutions that we came up with. And I hope that that was useful to you. And that's the end of my talk. Thank you. And I think we have at least a couple of minutes for questions. I think the first was from Kevin. Yeah, it's WebSocket Gateway is our internal application, and it's largely internal because, as I mentioned, we just introduced the RSocket point as a part of an existing gateway, which is tied to Canva and tied to a lot of the application features. In particular, it's how we do authentication, authorization, and the rest of infrastructure-specific Canva functionality. Outside of compression, are there any techniques that Canva uses to reduce the amount of data transmitted? I think in the case of RSocket, it's pretty tricky to affect the data that's flowing through the WebSocket connection. So I don't think we use anything for WebSocket connections. However, for standard HTTP requests or for anything else, yeah, we actively use Cloudflare as our CDN, and it provides broadly compression and a lot of other techniques to reduce the amount of traffic. Sorry, Nick, I don't know why RSocket hasn't been picked up as much as it possibly should, but I think it should definitely gain traction sometime soon. That's my impression, because right now a lot of applications move into this world into this world where collaboration is essential, especially with the COVID situation. So, yes, also kind of like a requirement for modern applications to be collaborative, to give that ability to users to collaborate in real time. And RSocket is a way to provide your users with such a functionality. So I think it should gain in popularity. What kind of JS frameworks we use? And yeah, a backend engineer, so I can't really speak a lot for our front-end engineers, but I know that we use TypeScript, MobX as the state framework with React. However, I can't go into the details just simply because I don't know. Yeah, Arthur is asking about gRPC for not browser-facing configuration between our WebSocket gateway and the backends, and why not? And we currently use RSocket for streaming interaction as well on the backend, and that's because it's because essentially RSocket has already solved this problem in one part of the stack, and there is no real reason for us to introduce gRPC as a second library right next to RSocket, because as far as I can tell, it wouldn't really give us anything, but it would definitely introduce complexity because we would have to convert our interactions from one world, from the world of RSocket, into gRPC, while with RSocket it just neatly all connects together. Yes, RSocket is leveraged for backend service-to-service interaction, but right now we only use it for streaming specific interactions and not for request response. About the amount of data transmitted, thousands of items transmitted in the operation. Yes, RSocket, essentially it's a very efficient protocol. So I think the only limit for RSocket is the underlying transport protocol. Because RSocket is transport agnostic, the throughput of a single RSocket connection primarily depends on the underlying transport. So essentially, when we talk about RSocket in the context of a browser tab to a backend interaction, we are talking about the underlying transport, and in that case, about WebSocket. And when we talk about two backends talk to each other, it depends on the underlying transport again, which can be either a WebSocket connection again, or a plain TCP connection. And in that case, yeah, the only limit is the underlying transport. Yeah, there is another question about conflict resolution. And there is definitely, we have a separate service that implements conflict resolution on various deltas for the changes. Again, I can't really go into the details because we have a separate team who is working on that service. And I'm on an infrastructure team that provides a transport for this service. But unfortunately, I can't go into the details of conflict resolution because, yeah, again, I don't really know the details. I know that a lot of maths is involved. There's another question about using RSocket for real-time model serving. And I think if I understand the question correctly, it's about machine learning, and maybe somebody can help me answer it because, yeah, I'm not really familiar with the machine learning domain as much, so I probably wouldn't be able to answer this question. Does the stream termination when a service is deregistered with the gateway affect the client? Yeah, that's a good question. Essentially, every time a backend gets removed from an auto-scaling group, it gradually closes all of its channels, and that way the clients would reestablish the channel on a second try again. And all of the clients are implemented in a way that would retry channel creation or the whole connection creation if the connection shuts down. And because of that, essentially we do mitigate impact that every time an instance goes out of service, it gradually closes all of the channels and not all of them at once. But also, every single client knows how to reconnect. There's a question manage and what we use to store or manage. Don't use anything fancy. Can I use a web server that takes the incoming WebSocket connections, and the WebSocket gateway would essentially propagate these connections further to the downstream services and would establish this two-way channel, and then the messages would just fly back and forth. If something happens and the channel gets interrupted, then the clients would reconnect. And we have to, just to clarify, all of the clients with WebSocket connections have to know how to reconnect, because we can't know anything about the network conditions or the state of any intermediate proxies. For example, if I close my lid right now, it's likely that my laptop would close the connection, and when I open, I would still see the browser tab, and the code on the client side would have to reconnect so that I can continue my session. How the UI manage to register just for data it needs to be notified for? RSocket provides you with the interaction model based on channel. Essentially, on the client side in the TypeScript, I can say I request a channel with this particular service, for example, with editing service for this particular design. And that way I would get back a channel on which I can subscribe, and I can listen to all of the incoming messages, and also I'll listen to when it gets completed, either successfully or with an error. And that way, I submit a request for a channel with the metadata on what exactly I'm requesting, and then I subscribe on the response and listen for all of the incoming messages. There is another question on how many open connections we handle and how many service instances under load balancer we scale up. For it, it's not sure if I can answer that. I would need to clarify with someone probably whether I can mention the total number of connections or not. But essentially a single instance, we prefer to use a large number of smaller instances. So right now we use actually a container with 2 cores, which is essentially an equivalent to a simple M5.large or R5.large instance, which essentially gives you 2 cores, and I don't remember either 8 or 16 gigabyte of memory. I think right now it's probably 16. And we prefer to just have a lot of them rather than having just a few smaller and beefier servers, because in the cloud, you never know if something can happen to one of them. They sometimes just go blank, they just hang, and reachability is lost. And every single one of those servers is currently handling up to 50,000 concurrent connections. And we scale up when, essentially the average number of connections crosses the threshold across the whole fleet. Would WebSocket be the most suitable transport protocol? Does Canva to move more suitable quick particular. I think it heavily depends on the type of interactions, and in my understanding that quick, yeah, I'm not sure I know quick very well, and but in my understanding, WebSocket gives you a higher level of interaction that can potentially be backed by another protocol, and maybe even WebSocket over quick one day. I'm not quite sure what's the state of this right now, but for typical request response interactions, we do use HTTP 3 from our browsers to the edge. And for streaming on just plain WebSocket, because it's kind of like, yeah, it's what we want. We have a simple connection that works as bytes in, bytes out. Yeah, and I think these are all of the questions, but if you have any other questions, feel free to, yeah. Did we start Canva on RSocket, or did we use something else before? So essentially, when we first started designing transport for this particular functionality, where this would be a requirement, having bidirectional streaming, we considered multiple alternatives, in particular like classic techniques like long polling or server-side events, and all of them had some particular downsides. And WebSocket was the obvious answer that gives you the exact solution that for the exact solution for the problem that you have at hand. However, with WebSocket, you need to understand how you would handle multiplexing, and because we can't create 10 connections from our browser tab for 10 services, when you handle millions of concurrent connections, it quickly adds up. So in that sense, we needed some protocol that would give us these guarantees and would also provide some form of backpressure, because once you have a single connection, you've got different services competing for the same connection, competing for the same resources. And in that sense, RSocket was a really good choice. We also considered gRPC web and similar techniques, but I believe it works. It doesn't quite give you the right abstraction. And when we first looked at it, it wouldn't even give you a bidirectional streaming, only unidirectional one. I think Emily just sent a message that I have to wrap up, and the separate session would begin in 2 minutes. But yeah, if anyone have any more questions, happy to answer. Thanks. Okay, I think the next session has started already, so I'll also join. So thanks everyone for joining me today. But yeah, if you have any questions, feel free to message me on Twitter, and yeah, I'll try to answer all of them. Thanks. See you guys.